Welcome to Chapter 9. This is our last section and last part of that section. So we're still in Section 3, and we're now talking about heating curves. So what we're going to do is we're going to learn how to interpret, which means understand and share the meaning of the various sections of a heating curve. So a heating curve is just a graph of the temperature of a substance and the amount of energy added as it changes phases. Now remember, a change of phase is when things go from a solid to a liquid to a gas, or it may go the other way around, from a gas to a liquid to a solid. So that, remember, is a change of phase. So now I want you to pause here for a moment. Okay, and I want you to draw, and you need to draw this in your notes, what you think the graph of adding heat to water as it goes from ice to steam looks like. Okay, so a couple hints. Water freezes at 0 degrees Celsius. It boils at 100 degrees. When you draw your graph, okay, it should look, this is what the basis of your graph looks like, right? You've got your two axes, and you should have the heat added here in joules. Okay, so increasing heat. And this axis here would be your increase in temperature in degrees Celsius. So go ahead and pause and do just that. All right. Hopefully you finished by now. Hopefully you actually hit pause and drew that. And now let's look at what an actual heating curve for water looks like. So water's actual heating curve looks like this, and you can find it on page 317 in your textbook. You can see that here. It kind of overlapped these a little weird. Sorry about that. So let's take a look at this heating curve now and see if we can start to figure out what it means. So we have several parts to our heating curve, and this first part here that I want us to look at is right here. We've got this part here, and that is a point when you have ice. It is a solid. And we're adding heat going this way. It's hard to see. I'll write that down here. This way we're adding heat. And as we add heat, we get to this point where we have ice and water mix. Okay? Then it continues as we add heat and we get water. Then we'll have water and steam, and then we'll have steam here. So here and here, we have a change of phase. So now let's pause and look at a slightly more generic one. So this is the same thing. We still have an increase in temperature going this way and heat being added this way. But I want you to tell me a little bit more about what is going on at these flat places. So we've got this flat place right here, this flat place right there. I already told you it's a change of phase, but why are they flat? Okay, go ahead and write down what you think the answer is to that question. Why is it flat? Okay, and then tell me what is happening at these angled places too. So go ahead and pause, and I just want you to think about it, okay? And think of it in terms of the temperature increase here and the heat being added in joules, and write down your answers. So go ahead and pause again. And now let's look at what those actually mean. Hopefully you have your answers written down already. So when we look at this heating curve, and again this is for water and it's in your textbook, okay, we've got ice to begin with, and then we get ice and water. And while it is changing phase, okay, we have both ice and water at the same time, but notice the temperature has not changed. The flat place means it stays at 0 degrees Celsius. So here if we look at this value and this value, we have added a total of 3.3 kilojoules of energy. Okay, but the temperature has not increased. And then if we look over here, this is now at 100 degrees. Okay, this point here is at 100. And we get the same thing going on. We've got this large flat place and this little zigzag. You guys see the zigzag? That zigzag just means it should be spaced out a lot more, but they wanted to make it smaller to fit in the graph. But here we've gone from 8.04 kilojoules to 30 kilojoules. So that's a difference of 22.6 kilojoules. That is a lot of energy that is not increasing the temperature. So what's happening there? Well, what's happening is, remember, a solid is all about particles being locked in place. They can't move. They might vibrate a little bit, but they are stuck in place. Now, as we increase their average kinetic energy, okay, they start to move around, and they become a liquid, right? And they fit in a glass. They take the shape of their container, but they're not locked in place anymore. So as we do that, the average kinetic energy here is increasing quite a bit. But there's also energy going into releasing them from their locked positions. Okay, and the same thing happens when we go towards a gas. We've got this liquid here, and now you've got particles that are shooting out, okay, flying off as they become a gas. And so some of that energy goes into releasing those particles, okay, turning them into a gas, turning them into a liquid. So that's where all of this energy goes. It goes into that change of phase, but the temperature doesn't increase. So the whole time that you have water and steam both, the water and steam are both sitting there at 100 degrees Celsius. Sorry about that, bell again. What I was saying is the water is sitting there at 100 degrees Celsius with this steam. And the same thing happens when we have the ice and the water. Even though some of it's water and some of it's ice, they're both sitting there at 0 degrees Celsius. So all this energy, we have a specific name for this kind of energy that causes the change of phase. Okay, and that is called latent heat. So latent heat is just the amount of energy added during a phase change of any material. We use a variable L as units of energy per mass, which is joules per kilogram. But we actually won't do any calculations with latent heat. But you should know what the variable is, what units it uses, and what the definition of the word is. So our last thing then for today is I just want to point out that we can talk about the latent heat of fusion. Okay, so latent heat of fusion, I'm just going to write that L of. Okay, so L stands for latent heat. Latent heat of fusion is when things are turning from a solid to a liquid, or a liquid to a solid. And then we have the latent heat of vaporization. Vaporization, like to become a vapor. So a vapor is kind of another word for a gas, and it tends to specifically mean water, but we use it for other things. So that's anytime you're changing from a liquid to a gas. That is vaporization. So latent heat of fusion and latent heat of vaporization may not be equal, and they will all be different for different materials. So that is the end now of Chapter 9. We have finished it. Hopefully this video isn't too long, and I will see you guys in class. Let me know if you have any questions.